right, so we finally reached the last lecture of the course, and we want to continue to introduce distributed computing and parallel computing in the field of deep learning. So I believe many of you are, have learned, maybe self-learn or took some classes to learn deep learning, and you probably have some knowledge about deep learning already. But I promise, what you learn is completely different from what we teach here, because we are talking the subject from a completely different point of view. We are talking about deep learning from the computing side of the application, right? How we could perform those deep learning computation efficiently with the help of distributed and parallel computing techniques or system. Okay, so there's the so those knowledge are usually not covered by the traditional deep learning class, because all those class probably more focusing on how you design and develop the deep learning model, right? And you probably only need to know how to implement your model on some deep learning framework like PyTorch and TensorFlow, and you probably don't even need to know what happened you know through those frameworks, right? You probably just as a programmer. Okay, but if you want to make sure your computation is efficient, and you can do that across a data center, right, or on GPU, then that's the topic we will cover in this lecture. Okay, so actually we have a lot to talk about, and we only scratch the surface of the problem by let you know how important is the power of distributed computing and parallel computing. Because as a matter of the fact, deep learning in some way is driven by not just data, but also computing power. And the computing power, you can only obtain that through distributed and parallel computation. So we could connect that to what you learned from this course, right? By how you can do that by using GPU or other distributed computing systems. Okay, so we will cover a little bit, how GPU is supported, how GPU support deep learning, how you can do distributed deep learning for training your model, and how those framework um, to provide distributed computing. So how you can actually do distributed computing through TensorFlow or Horovod, those library. Okay, we will arrange a lab. Okay, we still keep this lab for you to be able to just experience how to run distributed learning, how to train a model distributedly across machine through TensorFlow and Horovod. Okay, and finally, actually more importantly, is in general, the topic we cover right now is already formed a new research community called ML system. Okay, so actually people already find out that if you want to provide a production solution, a production AI solution, the most of the problem you face is not on the model, but on the system side. Okay, so how you could realize those, how you could collect data, right? How you can train your model efficiently, how you can deploy your IO solution on cloud or on edge device, how you could maintain the service, how you can automate all the management efforts with the minimum human intervention. Um, all those are the critical problem we are facing now. So we will just mention a little bit of the problem, right? Some of the problem that people already start looking at. So there are still a lot of research and engineering or um, problem to solve from both academic and industry. Okay, so that's why already become a new community, and it start getting a lot growing attention from from everyone. Okay, so we will mention couple of technique like what is auto ML, what is AI chip design, what is federated learning, um, all those bathing word uh, are related to ML systems. So at least we would like you to recognize or aware of those problems. Okay, not just focusing on designing a model or just thinking about how to train a model, how to tune the parameter. Um, and there are a lot more problems exist. You need to overcome in order to provide a real AI products. And that's exactly why even today, AI still considered to be, maybe a bubble or is still a technology that's unproven. We still don't see many, scalable or viable solution from AI because we still don't have the complete solution for make it become a production. No, make it become a productive and production solutions. Okay. All right. So anyway, actually um, there are still require a lot of techniques to be developed in this field. Okay, it's not just about the algorithm. Okay, all right. So first of all, what is deep learning? I think many of you already have the idea, and it's actually deep learning is a specific uh, class of algorithm for realizing AI, right? Artificial intelligence. And so AI is the end goal, right? Is the global is the biggest problem we want to achieve, right? And it refers to any techniques that makes the human can react and behave like a human. So there are many solutions to achieve that, and a class of a solution that try to the class of algorithm that driven by data is what we call the machine learning. Okay, so it means algorithm is learn from the data. You can automatically derive the algorithm by the machine, right? So it's driven by data. Okay, so it's just one type of algorithm that can achieve AI. And deep learning is a subset of a machine learning algorithm because deep learning is specific referring to the algorithm that based on the artificial neural networks. Okay, so there are again many ways to do machine learning, but deep learning specific referring to the learning technique based on artificial neural network. So that's why when you hear about AI, you should not assume that the algorithm is it's a neural network. It maybe it's not because and deep learn and the neural network or deep learning also not guaranteed to be the best solution for AI because it all depends on your problem complexity and your data, right? But however, the reason surge of AI is because of deep learning. Because people find that through deep learning, it's possible to solve many problems with very good, accurate results. Okay, because of the power of data and computing. Okay. So So, and also because no deep learning is a universal approximation. According to universal approximation theory, with neural network you can construct a network that accurate represent any function in the world. So when we say AI, it's basically like a function, right? We throw an image, in return, what's the image, right? So it's just potentially just a mapping function, and deep learning is the one that can perfectly represent any function. So supposedly, um, it should be the most accurate function. So and also the most general and most powerful, okay, because it can fit to solve any problem, right? And however, this is so powerful because of you require lots of data, right? So the reason deep learning becomes so powerful because now we finally have the enough size of the data because of the big data era allow us to collect enough data to drive deep learning. And deep learning itself has many other strengths, like we said, it can adapt to a very wide variety of data or problem, right? Because anything anything that can be characterized by data, we can fit those data to train a deep learning model, and in order to solve the problem. Okay, so it can apply to potentially any application domain. And the neural network is actually a structure, is a structure model, right? So when you design a model, sometimes you don't really need many statistical training, right? It's a modularized solution. So you can just combine two network together to construct a new model. So it doesn't require very high bar to enter this field in some sense. Okay, and you can have a lot of flexibility because you can combine those network in any way you want and to get some result. However, for some traditional machine learning algorithm, we know you cannot just arbitrarily change the equation, right? It They have mathematical theory or behind it, so you cannot just arbitrarily change the equation. But for neural network, you could do that. It's not guaranteed to get a better result, but it can get results. Okay, anyway, you can get results. It's easier. You can you can construct the network in a modular manner. So it's you have more flexibility basically. Okay, so that's why you know we have things so many different neural network model proposed in recent years, and most of the time, many of them actually cannot be proven by math, right? But they validated by some of the data. So um, you can still claim to have a new solution and to claim it maybe it's a better solution for some specific problem. Okay. So anyway, we have more. We have many. We have a large, much more room to grow for deep learning. Okay. All right, and potentially any model, if you have more data, then you can expect better results. So that's why sometimes it's maybe it's very simple to use a, DL solution because all you need is data, not the network. Okay, so you can use very simple model with to solve a problem if as long as you have enough data. Okay. All right, and if you compare deep learning to the traditional machine learning algorithm, the biggest difference is for traditional machine learning algorithm, usually it required users to do the feature extraction. It's important to feed the correct feature to the algorithm to get a good result. But for deep learning, even the feature itself can be learned from data. So uh, it's more powerful. But of course, the cost is you require even more amount of data in order to learn the feature, right? And sometimes you may get incorrect result because you try to learn the wrong feature. Um, so in practice, still, even with the deep learning algorithm, people still uh, need to do feature extraction or at least to understand or even customize the feature for those deep learning solution. Okay, you cannot just entirely rely on the data. In short, okay, all right. So it's not surprise, right? Um, with the characteristic of deep learning, people keep try to train their model with larger data set, and people try to increase the scale or the size of their model. For example, simply having more layers in their neural network, and people want to train their model with more iterations because sometimes uh, if you train long enough, then you can just keep increasing the accuracy, right? So you have to train the model with enough iteration, and finally, there are so many parameters exist in deep learning, in the training of a deep learning model, right? For example, maybe the learning rate, the dropout rate, the number of layers, um, how to select the features, etc. There are many parameters that can be controlled to train the model, and maybe more than hundreds of parameters. So if you want to get the best result, that also means you have to go through those parameter tuning process. So as we know now, in order to get the best result, usually people have to keep retraining their models with different tuning parameter and see which one give you the best results. So um, no, at the end, all those things require computing power, right? So you can imagine the the requirement, the demand of computing for deep learning actually grows in a very fast, rapid pace. As a matter of fact, according to the survey from the very famous OpenAI, AI lab, shows that the growing rate of computing demand from deep learning actually grows even faster than the Moore's law. So you can see this is the log scale, and this is the amount of computing capacity you need in order to train the latest model at that time. So you can see this line, shows until almost 2019. For example, Alpha Go zero, right? The amount of computing power is already several times over AlexNet. Right, the increasing speed is actually 3.5 months. Every 3.5 months, you will double the computing demand. Okay, so that's actually much faster than Moore's law. Okay, so that's why we said deep learning actually driven by computing power in some sense, and also data. If you have those two, then you probably can you probably need those two in order to actually get a good result from some deep learning model. Okay, so how is it possible, right? It's growing even faster than the Moore's law. So how human can break that barrier? And the reason is parallel computing, right? No, so we already know GPU. So as you know, for GPU or some SIMD processor, actually it can easily double its computing power by squeezing more computing core. right? So that's why the performance or the computing growth of those device like GPU actually grows faster than the Moore's law. Okay, and so it become a necessary technique. Parallel computing is actually a necessary skill or technique, right, to power deep learning. Okay, so you can see that in this graph, you can see just in the past 10 years, uh, the computing power of GPU already grows, more than 1,000 times. Okay, so that's why we can match the demand of deep learning. Okay, and that's why GPU become really important for deep learning. Okay, but even GPU sometimes is not enough. If we want to right to obtain even more computing power, then sometimes we have to look for some more advanced or different computing architecture. Okay, so the TensorFlow, okay, although the Tensor Core is example of that. Okay, so what is a Tensor Core? So a Tensor Core is actually a hardware. No, it's a core, but it contains a very simple logic that only do one thing, one operation. That is this operation, right? D equal to a matrix A multiplied by matrix B and uh, add matrix C. Okay, and you can see this is just a specific computation. So we can use some hardware logic to create an aesthetic to create a chip to just perform this computation in one with one instruction. Okay, so this is much faster than GPU because you can see the matrix is two-dimensional. Okay, so that means the tensor core has the ability to process a two-dimension operation with a single instruction. Okay, in comparison, for GPU, if you remember, GPU is only a vector processing, a vector processor. So for the same operation, okay, if you use GPU, you have to compute it one row or one column at a time. So this operation needs to break down to several GPU instructions. But with Tensor Core, no, this can be done in just a single instruction. So basically, we extend the parallel computing from one dimension to two dimension. So of course, just like CPU can only perform the operation on one element at a time, GPU can perform the computation on one row or one column at a time. Tensor Core can perform an operation on one matrix at a time. So again, it will be much faster than Tensor Core will be much faster than GPU. But again, it has more strict limitation, right? Because Tensor Core can only do this single operation, nothing else. Okay. But why we design Tensor Core? Because for deep learning, probably 90% of the code is to do convolution. And what is convolution? Convolution is done by this operation. Okay. So basically, to train a deep learning model, you keep repeating doing this operation. So we might as well just design a chip that specifically do this operation with the highest efficiency, okay, or highest performance. Okay, so that's why uh, today you have this similar. This is just a core. This is just a chip. So this is already integrated to GPU, or some of the CPU also integrated with this kind of core as well. Okay, because this is just a you can think as an accelerator of an accelerator. Okay, so CPU, GPU. Today's CPU and GPU, they are both sometimes will integrated with a solution like tensor core. Okay, for deep learning. Okay, so this only work for deep learning or computation that match to this operation. Okay, all right. So this is a trend for hardware. Basically, today, in order to achieve or reach even higher performance, we still require hardware, and we have to have those specific design hardware for specific computing. Okay, computing behavior. Okay, so clearly with Tensor Core, now we can run much faster than CPU or even GPU. Okay, so that's why it become popular. Okay, all right. And so, however, for GPU, you can see to to obtain computing power sometimes is easy because you can just customize your processor, right? Or you can just having more processor inside your or more cores inside your processor to have higher computing power or computing capability. Okay, uh, so as a result, today usually the bottleneck is not on the computing side, but the data access side. Okay. For example, just like your homework three, when we teach GPU, we keep saying the real bottleneck of GPU is on memory access, right? So even though you have Tensor Core, a solution like Tensor Core, uh, it will actually just no um, escalate the problem of memory access. It's not mitigate or reduce the problem. It's actually increase the problem. Okay, um, so that's why the memory access is become an even more urgent problem we need to solve for a solution like GPU. Okay, and how it solve it is that, of course, if it's inside the GPU, then we can use some of the technique like 3D stack memory to increase the memory bandwidth, reduce the memory latency. But another problem is, as we mentioned, is the data transfer bandwidth between the GPU card or between CPU and GPU. And the traditional um, computer uh, rely on PCIe bus, right? Which is already exists for forever. So the bandwidth it can provide is also very quite limited. So that's why a company like media, they design their own bus to transfer the data between GPU or between CPU and GPU. And their solution is called the NVLink from NVIDIA. Okay, and the idea is basically provide their own bus, okay, to directly connect between their GPU, so it could achieve more than 10 times of bandwidth than the traditional PCIe bus. Okay, and so just to let you know that to provide NVLink, right now there are two ways. One is um, to entirely go through a different fabric or link across the GPU card. So in that case, even the GPU need to be, it looks different basically. So it's not the car you think from the shop. Okay, so it actually looks like a chip over like a chip showing here. So this is what we call the SXM module. So if you look at this NAND, this is a NVLink that tightly integrate with the GPU card. Okay, and it require a different basically motherboard at all, no, all together. So if you don't want to replace your motherboard, you still want to stick with your machine based on PCI switch, but you want to have an NVLink, then there's another product called the NV Bridge. So the NV Bridge is you can look up from internet. It's basically uh no you can say it's a like a line, okay, a link. It's an external link that can connect between the GPU. Okay, so the GPU still go through the PCIe box, the PCE bus to connect to the motherboard. But between GPU, you have this bridge to connect between the GPU. So if you want to transfer data, you will go through the NV bridge. But if you want to control the GPU between your host and device, then you will still go through the PCIe bus. Okay, so NV bridge is add-on. You can say an add-on solution on a regular machine to 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 provide this NVLink solution. So it's usually cheaper, but performance will be lower than the 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 SMM module showing over here. Okay. Well, anyway, so there are a lot of change happening over the past few years to provide performance to solve this uh, memory transfer bottleneck. Okay. So this link, as we mentioned, mostly is connected between those GPU. Because if you want to connect between the CPU, you need to modify your motherboard, need to even modify the CPU. So um, most of the CPU model doesn't want to change for certain GPU card. So that's why even with the NVLink solution, it's usually just provided the transfer across GPU for peer-to-peer data transfer. Between CPU and GPU, usually is still very, very slow. Okay. So again, communication is important for parallel computing. So it's no surprise that with NVLink, you can see many performance plots to show it can provide a much better scalability for the parallel computing application, right? This is scalability is what we care for parallel computing, especially in larger scale. Okay. So finally, so you can see when we say we use GPU for deep learning, it's not just the GPU card. Most of the time, especially today, it's system integration and system optimization at every layer, from storage, from computing to communication, from hardware to software stack, everything. A company like NVIDIA, they provide those uh, no, end-to-end solution like DGX2 server. So it not only can install many GPU cards, but it also provide like solution like NVLink, integrate with NVMe SSD, infinite band, everything we talk about for high performance computing or supercomputer. Basically, this single server is pretty much like a supercomputer. And of course, as we mentioned, uh, today's supercomputer, many of them are built from a GPU server like the one we think here. So um, this is the how we could have those computing power. Okay, and finally for Taiwan, that's why for every country it's the same thing. In order to develop their AI solution, we all know the future world will be controlled and driven by AI. And in order to do AI, you need high performance computing. So that's why we see most news going on, right? Very unfortunately, but that's what happened. What happened, right? That's the world we're living in, right? People really try to control um, high performance computing because that control AI and control the world. So those computing power is really important. So for Taiwan, it's the same thing. Back in 5 or 10 years, when we talk about AI, the very first thing is to build those AI systems or supercomputers. So that's why we have Taiwan NEAR 2, and today we already have the third generation of Taiwan NEAR supercomputer. And So the purpose is to drive AI solutions. Okay, and our supercomputer also built from the solution like DGX2. Okay, so that's why we can deliver those computing power. Okay, all right. So that's just the hardware side, and we will continue talk about how to enable deep learning or how to power deep learning from the software side. Okay, so we will talk about those libraries that needed to uh, to do the deep learning. Okay, all right. So that's it for today's lectures. Okay.